you all so very much for joining us today. This is going to be a beginning of several different uh, videos that we're going to do on DSP.
Nick, unmute yourself, please.
Okay. I don't know what's going on. Every time you mute, it mutes me.
Yeah.
Okay. We're learning. So anyway, so the way that this is going to work today is we're going to go through each individual filter type and how best they are to be used. And we're also going to be discussing an awful lot of interesting things that I get a lot of questions on in technical support. So the first thing we're going to talk about are the types of the active systems to design. Then we're going to define and understand the filter types that we use when we're designing those systems. We're going to talk about how we actually choose all of the crossover points, those frequencies, and why you want to use them. Then we're going to be talking about selecting which style of filter to use. And then we're going to talk about using the EQ. And so to get started immediately, obviously we need to determine what type of active system you're going to be designing and building for somebody's system. There are four basic types that we're going to be working with today. The first one will be a completely passive system. That means, we're using the passive networks. We're going to be building basically what is known as a high pass filter for them, whether it's a 6.5-inch two-way, 3-way, or a coaxial 8-inch two-way. If we have a passive network in it, we're going to be talking about that. The other one we're going to talk about is an active two-way. That would be a 6-inch, 6.5-inch, 5.25-inch, 8-inch with a tweeter. We'll have a three-way. Obviously, that would be an 8 and a 3 and a tweeter, or a 6 and a 3 and a tweeter, something along those lines. And then the fourth one would be what is known as a semi-active system. That's a system in which you're going to be using passive and active at the same time. And the goal here is for you to be able to design and build a system such as what you're looking to your right. This is a system that I designed for somebody about 6 months ago. As you can see, this is a very complicated system. It's a fully active three-way in the front with a center channel. That's a 3.5 in the tweeter. You've got a pair of coaxials for the rear and a pair of subs. This would be probably one of the most hardest systems to design because this involves everything. You're looking at a semi-active system, fully active system in every respect. So the goal is for everybody to be a little more comfortable to be able to design and actually build something like this. So system number one, we're going to be using our passive networks only. And this is where we're going to use basically only the high pass filters. So, this is where we have coaxials, we have separates. You can see the passive network in the 165 FXE. And this is where you would be using a Mosconi, such as a Mosconi 1 40-weight DSP. This is a very simple system. It's a very easy system to design and build. Only thing we're going to need to worry about here is how low we're going to let the 6.5-inch mid-bass drivers in the front and in the rear are going to play. That's a very simple system, very easy to understand. System number two would be a fully active three-way system. Now, this requires the use of high pass and a band pass. And if you take a look at, in this particular instance, we're going to be using a Focal TBM tweeter. We will be using a Focal 3WM, and we'll be using a Focal 8WM. This is a very great, really nice sounding system. Now, to get this to work, you're going to need, obviously, 6 channels of amplification with 6 channels of DSP processing. And obviously, a Mosconi Pro 8 to 30 would be ideal for this. You would use a high pass on the TBM tweeter. You would build a band pass for the 3WM, and you would build a band pass for the Focal 8WM. That's where the three-way comes into play. System number 3, this is going to be an active two-way, and this is going to require a high pass and a band pass as well. Obviously, we have a FRAC tweeter. We have a 6.5 km. And again, you would be using something along the lines of a Moscone 148 DSP. This gives us 4 channels of amplification. It gives us 4 channels of digital signal processing, and it allows us to put a high pass on the tweeters, and it allows us to put a band pass on the 6.5 km. The 4th system is semi-active, and this is one that I get questions on a lot with, especially on the end users, because this requires the use of a band pass. This is where you will take something like a 165KX3, and you're going to use a combination of the band pass filter on the 6.5-inch mid-bass drivers, and then you're going to come out of the amplifier and go into the passive network and have the passive network control the frequencies that are going to go to the mid-ranges and the tweeters. This is a combination. This is the reason why you would use an amplifier such as this, because it gives us numerous different abilities to do what we need to do, such as if you wish to bridge channels to put on the mid-bass drivers, for instance. Okay, so these are the systems that we would be using. And obviously, we're going to be talking about that if you want to add rear channels to an active two-way or an active three-way. If you wanted to add subwoofers into the system, obviously you can do that. It would be adding a low pass or a band pass as well into the system. So obviously these filters are important, and understanding what these filters are. And so now that the system design is complete and we have an understanding of what a two-way and a three-way is, let's determine what type of filters to use. So if you take a look at this filter in particular instance, okay, there are these different ones that we're going to be using. We talked about a high pass, we talked about the low pass, and we talked about the band pass. These are the 3 key ones that we're going to be using to build any system, okay? So first one to take a look at is going to be a high pass filter. And by definition, a high pass filter is an electronic filter that passes signals with a frequency higher than a certain cutoff frequency, and then it attenuates signals with frequencies lower than the cutoff frequency. Basically, what you're looking at is right here. This is a 12 dB per octave slope, high pass filter at 2000 hertz. And what it's doing, it's just allowing frequencies above 2000 hertz to play out all the way to 20,000. Whereas below 2000 hertz, it is attenuating the frequencies, or it's cutting those frequencies off. That's what a high pass is. Now, I know a lot of you out there thinking, Nick, this is rudimentary. Why are you talking about this? Well, believe it or not, we have dealers that will call, and we're talking about putting filters on tweeters, and invariably we will find out that they have put a low pass on the tweeter, and because they don't understand what filters are doing what. It's the reason why that we're talking about this. So understand that with tweeters, you really want to use a high pass on them. If you want to build a low pass on the tweeter and tell it you don't want it playing above a certain frequency, that's up to you. Why you would do that, I'm not sure, but I know some people that do it, and that's up to them. But this is the reason why we wanted to talk about this, because people get confused between a high pass and a low pass. Now, when to use this high pass filter? Well, there's a lot of reasons why you want to use this filter, okay? Number one, you want to use it because of tweeters. Obviously, with tweeters, you want to limit how low they can play, because we all know they don't have a very big voice coil, and we can blow them in a heartbeat, okay? And we don't want to do that. Number two, you also want to use them with an active mid-bass. Now, everybody asks me, well, why do you want to put it on a mid-bass driver? Well, we only want the mid-bass driver to play so low. You know, if we let it play as low as possible and we get close to where the voice coil loses control over the speaker, we have a really big chance of actually blowing the driver. So we don't want to do that. Obviously, if we're building a three-way, we want an active mid-range. That, you know, obviously in the mid-range, you want to make sure that it only plays like in the mid-bass. We only want it to play so low again, because we only have so much voice coil to work with, and we don't want the voice coil to blow up. Then there's also going to be this, what is known as a semi-active passive system. Again, so like with this particular instance, we have a passive network, but we only want the mid-bass drivers, again, to play only so low to protect them. So that's the reason why you would want to do that. And finally, and a lot of people forget about this, is we want to use it with a vented subwoofer system. When you have an amplifier with built-in DSP, more than likely you don't have a subsonic filter built into the amplifier with the DSP. So you want to make sure that when you have a vented system that you know what the tuning frequency is of the enclosure. And you want to add a subsonic filter to it, which is basically a high pass filter. Okay. A lot of what I will do as far as that is concerned, I will find out what the tuning frequency of the enclosure is. I would go 5 hertz below the tuning frequency, and I would add a 12 dB per octave high pass subsonic filter to it, which is basically what we are creating. Okay. So you can see there are numerous different times that a high pass filter is needed. Okay. Now, the other filter we're going to look at is going to be the low pass. And by definition, I will tell you the low pass is just an exact opposite of the high pass. It allows frequencies to pass that are a certain cutoff frequency, and they're going to attenuate the signals with frequencies higher than the cutoff. Basically, what happens is like right here, you're looking at a 2000 hertz low pass. Here's the 2000 hertz. Any frequencies lower than 2000 hertz are passed through. Any frequencies above 2000 hertz, they are literally cut off. They are attenuated. That's all a low pass is. Okay. Now, when to use the low pass filter? Anytime that we have an active mid bass. Really? Yes. Because if you have a two-way, you're going to play the tweeter from a certain frequency and out. And that means that the mid bass driver needs to take over for whatever that frequency is that we have selected for the tweeter. And it plays from, let's say, 2000 hertz and up and 2000 hertz and down on the mid bass driver for a two-way. And if it was an active mid-range, then you were going to do the same thing. If the tweeter is playing from 4000 hertz, we want the mid-range to play from 4000 hertz and down. And we also going to be using the exact same thing on a subwoofer. You know, obviously this is easier. Everybody understands that we're only going to play the subwoofers up to a certain level, a certain frequency, and then the mid-bass drivers would take over. This is when you would use what is known as a low-pass filter. So now the third filter is known as band pass. And by definition, it's a combination of high pass and low pass. That's all it is. And the design allows frequencies to pass within a certain frequency range, and it rejects frequencies outside that range. If you take a look at this one, this is a band pass from basically 2000 hertz to 300 hertz. This is a 4-inch mid-range. This is what we would be playing this from, as you can see from that chart right there. And that is a perfect band pass design right there. Now, to use band passes, this is, again, a fully active mid-range in a three-way system. We're only going to have the mid-range play so high, and we're only going to have the mid-range play so low. That's when the mid-bass driver will take over or the tweeter take over respectfully. With a fully active mid-bass driver, we're going to be doing the same thing, whether it's a two-way with a tweeter or it's a three-way with a tweeter in the mid-range. We only want the mid-bass driver to play so high, and we only want the mid-bass driver to play so low. So that's when you have to build the band pass. And again, with a fully active subwoofer, especially if it's a vented enclosure, this is when you build the band pass. This is when you don't have a subsonic filter on the amplifier. You build one within the DSP, and you have basically built what is known as a band pass for the sub. Okay. Now that those types of filters have been discussed, let's turn to crossover designs and the crossover slopes themselves. Now, crossover designs can be described in a lot of different ways, but for our particular discussion, when we start talking about them and their identifiable traits, we're going to start talking about the actual people who first used them, such as Professor Linkwitz and Dr. Riley, for instance. This is how we're going to be describing them. Now, those particular filters, and this is what they actually look like that we're going to be using. Within Moscone, you have what is known as a Chebyshev. And if you look right here, you can see that this filter slope right here, this is what Chebyshev actually looks like. The next one we're going to talk about is a Butterworth. This is the purple and gold right here. There will be the bezel, which is the green and blue, which is right here. And then there's Linkwitz Raleigh, which is right here. Now, what you're looking at here, these are all 12 dB proactive slopes, and this is in a perfect world what each one looks like. Now, as you can see, they basically do the exact same thing. They all basically attenuate certain frequencies. They can build a band pass with them, a high pass or a low pass. You can do anything with them. It's the shape of the curves that you see right here that matter, okay? And depending on what system you're designing, you would want to use these particular shapes and these particular filters. I have personally found for the last, and I've been building active system car audio for the last 30 years. One of the things that I have found that I really find works best is a Butterworth and a Linkwitz Raleigh. Yeah, the Chebyshev, which is this one right here that has this big bump in here where the crossover point is there a place to use it? Yes, there is, but it's rare. And I will tell you that I don't use it. I haven't used one in I don't know how long. It's there if you need it, because if you're at the crossover point and you're using, let's say, a Butterworth high pass and a Butterworth low pass, and they sum together and you get this great big huge nasty dip and you can't get rid of it, as chances are it's a phase shift. You might try the Chebyshev because of this boost that you see right here. It might fix it. It's, and I encourage you to play around with these. Get in the car, fire the system up, go listen to it, and actually just listen. That's how I learned. Just listen to how these things sound, and you'll get an idea as to what these things do and how they work. Bezel is very similar to Butterworth. If you take a look at the green and the blue, and then you take a look at the purple and gold, you can see that they're really similar in how they work and design. Using a bezel, again, I haven't used a bezel in probably 5 years. You can try it, and I do encourage you to try all of them and listen to them. But for me in car audio, I have found that Butterworth and Linkwitz Raleigh, they work best. And so for the following, we're going to concentrate on using Butterworth and Linkwitz Raleigh. Now, I will tell you, in order for these designs to work, there are 4 things that have got to occur. Number 1, all the speakers have got to be delayed correctly or time aligned correctly. That's one of the things that must take place, okay? So you want to make sure that all of the speakers are aligned and time aligned correctly. 2, all of the speakers really need to be close to the same output level. If you can get everything within plus or minus 2 dB, that's great. I've done it with plus or minus 4, and it will still work. But if you have a tweeter such as a Focal TBM that's like 95 dB at 1 watt, and you've got another speaker that you're trying to make it work, and it's at 88 dB, you have a problem, because the tweeter's producing way too much energy, and it will overlap the mid-range way too low. So you want to make sure that the output levels of those speakers are as close to each other as you possibly can get it. Another thing is that all the speakers should be used in a way that the free air resonance of the speaker does not come into play. And I'm going to explain free air resonance in just a minute. Also, it is highly desirable that the filters used in designing the crossover network be of the same type. For example, if we're building a two-way, okay, a tweeter and a mid-bass, if I'm building and using a 24 dB per octave Linkwitz Raleigh high pass, I want to try and make sure that I use a 24 dB per octave Linkwitz Raleigh low pass. It makes things easier, especially if you don't have Barney. Now, if you've got Barney, that's a different story. You can make things work. But if you don't, this way right here This makes life easier. Okay, so if you're using a 12 dB Butterworth on a high pass, try and use a 12 dB on the low pass and make it the same type of filter. It makes things easier trying to get them to phase align better. Okay. Now, as I said, I'm going to try and let you understand what free air resonance is, or FS. Okay. Basically, this is the resonant frequency of a speaker driver. And we don't want that to happen. We don't want any of our energy get anywhere near the free air resonance. And it's because at that particular frequency, it causes the most excitation of the speaker. That means the speaker can begin to distort. And the distortion is something we do not want to happen. The driver starts to lose control. The motor structure loses control over the cone, and we get tremendous amounts of distortion, and you can literally burn the voice coil up, which we don't want to do. And in this particular instance, this value is going to help us in designing crossover points, as well as tuning of the enclosures. That's where, when we talk about the free air resonance, FS, or the tuning frequency of a subwoofer enclosure, that's FS, same thing. So now, how do we use the free air resonance to determine a high pass frequency for a tweeter and the low pass frequency for a mid-range or a mid-bass? Now, this is how we're going to start designing the system, because we need to figure out how low or how high each one of these speakers can play in order for us to achieve maximum output with maximum clarity. Okay. So step number one, and for those of you who have your phones, if you want to take a picture of this, please do. There is a rule of thumb that we've used in home and car audio for many, many years. And I'm going to read this to you. For a tweeter crossover frequency, in order to ensure the safe and distortion-free use of a tweeter in active mode, the following rule of thumb is applicable, and for these will be for the minimum values. Now, what you're looking at is in the first four is you multiply 24 dB times 2, 18 times 2, 12 times 3, and 6 times 5. That is for home audio, or that's for a system in which somebody is not going to play a system loud. Well, we all know in car audio, that's not acceptable, because everybody likes to listen to it loud, because we have to overcome at least the road noise in the car. So 95 dB to 105 dB is easy. And that's the reason why, if the tweeter is going to be subjected to higher loads, because people like to listen to it louder, then you're going to have to increase that multiplication factor times 1. So if you're going to use a 24 dB per octave slope to protect the tweeter, you take the FS of the driver and you multiply it times 3. If you're going to use an 18 dB per octave slope, you multiply it times 3. If you're going to use a 12 dB per octave slope, you multiply it times 4. And if you're going to use a 6 dB per octave slope, you multiply it times 6. Now, I know everybody out there is thinking, who in the world is going to use a 6 dB per octave slope? I will encourage some of you to try. Get in the car and listen to the difference between a 24 dB and a 6. I think you're going to be surprised. Just go listen. And that's all I'm going to say. But just go try and listen to it. And you might get a really good idea that, yeah, you might want to try it one day. Not for the customer who listens to rap and hip hop and techno, but you just try it and see what it does. You're going to learn something really, really quickly. Okay. So this is one of the things we need to do in order to be able to determine our crossover frequency. Now, I'm going to give you an example. This is, we're going to be using a Gladen 28 millimeter aerospace tweeter. And this is the chart that is available from Gladen on this particular speaker. And you can get them for any of the speakers they make. And you can find out that the resonance frequency is 720 hertz, see it right here. So if we use the previous slide's formulas, there would be a safe crossover point to use in the crossover network high pass design for maximum power. And here they are. For a 12 dB per octave Butterworth, it would be 4 times 720. And for a 24 dB per octave Linkwitz Raleigh, it would be 3 times 720. Okay. Now, you can look on that chart, and I know that the cutoff frequencies that they recommend is 2200 and 1500. That is for a low-powered system. And I will tell you right now, please do not play a 28 millimeter Gladen Aerospace tweeter at 1500 hertz with any kind of power. Yes, it'll do it, but I will tell you, I don't like the way it sounds at all, and I don't think it's going to hold up very long. Mine right now, I have them crossed over at 3000 hertz, and they sound absolutely fantastic at a 12 dB per octave slope. Sound wonderful, absolutely fantastic. Now, there are other things that have to be taken into consideration when you're going to be building a high pass crossover frequency, and we're going to design it. Obviously, we need to take care of the FS of the driver. Absolutely. If you can measure, once the speaker has been installed in the car, if you can measure the impedance, if you have the tools necessary to do it, by all means do it. You may find that the free air resistance has risen. You may also find that the free air resistance has lowered. Okay. Now, use that. It's a great tool, and use it. If you don't have access, don't worry. Just go ahead and use what the free air resistance of the tweeters are, or the mid-range or the mid-bass that the factory says is, because I assure you, you're going to be in good shape. 2, you also have to look at what is known as the beam patterns for the mid-range or the mid-bass to determine the optimum frequency to use. For example, if like in my particular vehicle, I have an 80 millimeter aerospace driver, and I'm about to show you a chart, and we're going to show you that there are ways in which you need to determine when the speaker stops becoming omnidirectional, or it stops radiating at a 360-degree pattern, okay? This is called beaming. And what beaming is when you have a speaker that starts to approach a certain frequency. And because of the shape of the cone and the way that the speaker is designed, it stops being omnidirectional, or it starts to be able to where the frequencies start to narrow, and they become to where they fire straight at you or straight across the car. The analogy I like to give is this. If you've ever used one of the great big 6-cell flashlights, and you can rotate the flashlights, turn the head of the flashlight one way, and it floods an entire room with energy. That's an omnidirectional pattern. And then if you turn the flashlight head back to the right, or you turn it a different way, and all of a sudden it starts to narrow to where all the energy is pointed at one point on the wall, that's beaming. Okay, so that's what we do not want. We do not want that to take place, because what happens is that the speakers will be extremely difficult for them to phase together, to work together extremely well. So if you take a look at this chart, and I'm going to go ahead and go to this chart, okay? If you look at this chart to the right, you're going to see the approximate wavelength when a speaker begins to beam. This is when a speaker starts to have its radiation patterns narrow, and this is something we don't want to occur. Such as, if you take a look at the 6.5-inch mid-bass driver, the beaming limit is 2,672 hertz. Let's call it 2,600, okay? And if you take a look at the 3 and the 4, you can see respectfully, one is 4224, one is 5381. So if we want to get the radiation pattern of a 3.5, you add those two together and divide it by 2. That's like 4,800 hertz, okay? For 6.5, it's 2,600 hertz. This is one of the reasons I want to talk about this, is because if you have ever heard a two-way in a Ford truck where the tweeter's in the top of the dash firing straight up, and a 6.5 with a 6x9 on the door is firing, and they don't sound very good. And we've all heard that as many times as I've installed them, and a lot of you have installed them and listened. It doesn't sound very good. That's because the speaker on the top of the dash probably isn't playing down to 25 or 2,600 hertz. Most of the tweeters that are small enough to fit up there don't play that low. That's the reason why, because the 6.5, it starts to fire straight across the car, okay? They don't phase together correctly. This is the reason why when you see in a Ford and a Chevy, a Dodge, Toyota, that you see the 2.5-inch middler in the top of the dash, yeah, its radiation pattern allows it to play very low and very high. It'll play down into the 300 to 400 hertz range, which means it's going to make that 6.5 easier. That's the reason why they build that speaker up there. Okay, so this is something you have to take into account. And I'm staying on this for a minute so you can take a picture of this if you wish to do so. Okay, so to set the low pass filter frequency on the mid-range, remember we're working on the tweeter in the mid-range. As we selected 3000 hertz as the high pass crossover point for the tweeter, selecting a low pass crossover point is going to be really easy. If we check the beam patterns, we can see that the driver is at 4800 hertz. It'll work. So if I want to do this, if we're going to use a 24 dB proactive slope, go ahead and choose 3000 hertz. We know it doesn't start to beam until it gets to 4800 hertz, right? That's the mid-range. So I can choose 3000. It's omnidirectional below 4800 hertz. So that's the reason why we're going to do this. Okay. Now, if you're going to use a 24 dB proactive slope, okay, make sure that the frequencies are exactly alike. If we're going to choose 3000 hertz for the tweeter, choose 3000 hertz for the mid-range. Okay. It works really, really well, especially if it's a Linkwitz Raleigh, which this will be. It's either going to be a dual Butterworth or a Linkwitz Raleigh. Okay. Now, if you want to use a 12 dB, and that's fine, there's nothing wrong with it. If we're going to choose 3000 hertz on the tweeter, then gap the crossover point a third of an octave and take it to like 2500 hertz. Now, this is providing you're not using Barney. If you're using Barney, make them both 3000 and let Barney do its magic. This way, if you gap the crossover and you're not using Barney, what happens is if we're taking some of the energy that can build up between the two crossover points, they actually will have a plus 3 dB. They'll raise the output level at 3 dB at the crossover. If you gap the crossover, then it flattens it out a little bit, and it makes it easier to work with, and it makes it easier to phase. Again, this is another chart. It's just showing you, again, the beam charts. I want everybody to understand this. I want everybody to get a chance to use it. Also get used to looking at it, because this and the FS of the drivers, you'll be amazed how much better systems are going to sound if you follow these two directions. Okay. Now, as you can see with the chart, this is the driver we chose, and you can see the free air resonance is 110 hertz. This is where I found it. So if you take a look at that formula, okay, and our FS is 110 hertz, we're going to apply this also to the high pass filter. That's right. We most certainly are. So if the FS of that driver is 110 hertz, we're going to, and I want to use a 12 dB proactive slope, we're going to multiply it times 4, and that gives me 440 hertz. Okay. So from 440 hertz and up, I can use it if I want as a 12 dB proactive slope. Now, if I wanted to go to a 24, then I can use 330 hertz. Okay. Now, will it work with a 6.5-inch mid-bass driver? Well, absolutely, because the beam patterns don't start to narrow to 2,672 hertz, which is extremely high. So we want to be sure that the high pass filter is below 2,672 hertz and it is above 330 hertz. So in this particular instance, we're good. That means I can play it from 440 hertz to 3,000 without a problem. I hope everybody understands that. That's if it's a 6.5. So we don't have to worry about that. We're good. Our filter is at 440, so we're in good shape. And again, you can see it because of the chart right here. Now, when we're talking about high power handling, remember to multiply the FS of the mid-range times 4. And this is what it looks like. That's the bandpass we have chosen. So here's 3,000 hertz, and here's 440 hertz, 450 hertz. Okay. In this particular instance, I chose 450 hertz in my car. Okay. This is just an example. Now, the slopes and how to determine. I know right now people are asking, how do we determine which one to use? So let's talk about that. So in the crossover network, the slope is the rate at which the signal rolls off or it attenuates part of the crossover frequency. Okay. So slopes are known as the steepness of a crossover filtering ability. That's what a slope means. This is defined as dB per octave. Most commonly used in car audio is a minus 12 dB and a minus 24 dB. The steeper slope, 24 dB per octave, means that the filter characteristic looks more and more like a brick wall. And that means that we're going to be able to protect the driver, and we're going to keep the frequencies from playing from the free air resonance of the speaker. The shallower slope means that it's going to play more gradual, but that also means that we're going to get more output in the region beyond the crossover frequency. So there are times when you don't want it, and there are times that you do want it. And again, a lot of that comes down to getting in the car and going listening to it. Okay. So we want to make sure, obviously, that we stay away from the free air resonance of the speaker. So if you take a look at these two filters, these are perfect examples of a 12 dB per octave slope at 2000 hertz and a 24 dB per octave slope at 2000 hertz. So you can see here's 2000 hertz, both of them right here. Okay. And you see there's not a whole lot of difference right here as far as crossover is concerned. But as we get a shallower slope, you can see that all this energy out here is being played in this mid-range or this mid-bass or this tweeter. And yes, this tweeter, if this is a tweeter, you can see all the energy the tweeter is playing. Even though it's 30 and 40 dB down, it's still playing it. So at a higher slope, you can see that it's not, because the lower slope, you can see even down here at 30, 35 dB down, it's at 300 hertz. And at 24 dB, it's 800 hertz. So yeah, if you have a tweeter that has a higher free air resonance, let's say like 1000 hertz, and you've got a mid-bass driver that doesn't play that high, yeah, you're going to need to put a 24 dB per octave slope on the tweeter, and probably maybe a 12 dB or a 24 dB on the mid-bass driver at like 26 or 27 hertz. That's 2700 hertz. That's when you gap the crossover. It'll still work, but you need to be careful. This is the reason why you want to choose either a 12 or a 24, depending on power handling of each speaker. Okay. So there are reasons behind the 12 dB and the 24 dB. Okay. Now I want you to understand that what we're going to talk about right here, this is when they sum together. Okay. What happens is when you use a 12 dB per octave slope, okay, basically when they come together, you get a flat response. You really and truly do. Now, to get that flat response, you're going to have to shift one of the speakers 180 degrees out of phase. If you look on the Moscone GUI, you go look and you can see the phase section of it. All you want to do is invert phase on the tweeter to the mid-range, and you'll be just fine. Okay, if it's a three-way and you've got tweeter to mid-range and you're using 12 dB per octave slopes, and you've got mid-bass to mid-range and you're using 12 dB per octave slopes, you would invert phase on the mid-range. Okay, and that way what happens is all of this energy becomes flat right here, and it makes it easier for things to be in phase. Now, again, if you're using Barney, that's a different story. You don't have to worry so much about that. Barney's going to correct it for you. Now, reasons not to use it. Well, one of the things that we want to take into account is maximum output. Okay, when we have people that listen to things really, really, really loud, like 115 dB, 110 dB, 115 dB in that range, this is when I recommend do not use 12 dB. Please stick to a 24, because at maximum output, quite frankly, you're going to probably overdrive a tweeter in the mid-range. And we don't want to do that because that Burns voice goes up. Okay. Now, this is what an ideal Butterworth filter looks like at 12 dB. And you can see what happens right here. Okay. I'm showing you this because of the amplitude. These things sum together extremely well. And that's the reason why I'm showing you this, because it works really, really well. It actually sounds really, really good with a Butterworth 12 dB. Now, an ideal 12 dB Linkwitz-Riley filter looks like this. And they're like, wait a minute. There's a 12 dB Linkwitz-Riley filter. I thought it was only a 24. No, you're not. What happens is if you need to sum speakers together and one of the speakers has boosted energy, let's say at this 3,000 hertz crossover point, this actually is, if you take a look at the acoustic response in the car, you're running the RTA and you see all this energy and the tweeters playing all the way out to here. This is when you might want to choose a Linkwitz Raleigh 12 because it's a minus 6 dB versus a minus 3 dB with Butterworth. So all this energy out here can actually be turned down simply because of we chose that slope. And when you group them together, they're very, very flat. And it has a medium sensitivity to what is known as driver misalignment. Now that's taken into account that we're not using Barney. Okay, if you're using Barney, don't worry about it. It's going to correct for it. It's going to do the phase shifting for you at this crossover point. But if you're not using Barney, then you might want to use this and listen to it and see how it sounds or see how it sums together, because it may sum really, really flat. Because the optimum, what we're trying to do here is that when we build these crossovers, we get a flat response between the two. That's the whole thing in a nutshell. Whether it's a 12 dB or 24 dB, whether it's Linkwitz Raleigh or Butterworth, you want to make sure that when these two speakers come together, that they sum flat. That's the whole thing. Okay. So this is the reason why I encourage you to try different crossover frequencies, different slopes, and different alignments, whether it's Butterworth or it's Linkwitz Raleigh, and see which ones look better acoustically. You know, fire up the microphone, fire up the RTA, and take a look at it with pink noise. That's the easiest way to do it. Now, there are reasons behind 12 dB and 24 dB, which I just told you about. So I'm going to roll through this rather quickly. You know, the 24 dB proactive filters, they produce a minus 3 dB crossover point that sums to a plus 3. There are times you may need to do that. You may need that energy there because of the acoustic properties of the car. A 24 dB proactive Linkwitz Raleigh, which is sometimes called a squared Butterworth filter, produces a minus 6 dB, which we just talked about a moment ago. That's the reason why you may need to use that one. Both of these filters are excellent to use in a car audio environment as they create a wall that keeps the speakers from approaching free air resonance. And that is most important. We want to make sure that we stay away from the free air resonance of the speaker. The Butterworth filter, it qualifies for what is known as a constant power crossover. And basically what this means is that when the filters sum together, they get what is known as a flat power response. That response is the total of its on-axis and off-axis energy. In other words, the total acoustical output power is produced into the space of the car. These networks are extremely beneficial when the off-axis response to speakers is very important. How many times do we put speakers in OEM factory locations and we're playing them extremely off-axis? This is the reason why you may want to choose a Butterworth filter, whether it's 12 or 24, because of what is known as constant power crossover. It works extremely well because the amount of energy it produces off-axis. Okay, so take that into account when you're designing your system. If you're designing a system and you're using a lot of OEM locations, take a listen to the Butterworth filters and see what happens. Okay, so this is an ideal situation. When these filters are summed, you can see there's very little gap between the two of them, and you can see that this is going to be extremely easy to make things work because there's very little phase shift going on here. In the optimum world, there's very little phase shift. Now, if you take a look at the Linkwitz Raleighs, you'll notice there's a bigger gap here, okay, because of the shape of the filter. Now, there's reasons to use these, okay? You can see them. Now, at times you may need to do this, and I know this is going to sound redundant, but because if you have more energy, again, either in the tweeter or in the mid-range, and acoustically you see it playing way out here instead of rolling off naturally like it does here, okay, then you may need to use this type filter because it rolls it off faster, both of them, and it gives you a bigger gap right here so that the amount of energy that we're producing right here can be controlled better. That's the reason why if you need to use the Linkwitz Raleigh, you do it. because you've got a ton of energy between 3,000 hertz, let's say 1,800 hertz and 4,500 hertz. Use this one, okay? That's the reason why you want to use these. Now, this is a direct comparison, and you can see that there's a difference, and there's a dramatic difference between the two of them, even though this doesn't look like it. When these two come together and you listen to it, and I encourage everyone, sit in the cars, use your hearing, and just listen to the difference in the way the speakers sound using a Butterworth or a Linkwitz Raleigh. Okay, use a -12 and use a -24 and listen to how they sum. I cannot stress this enough. You'll hear what's going on, and you're going to find out really quickly which one sounds better. Because if it sounds better to your hearing, then I can guarantee it's going to sound better to the microphones. Okay, whether it's Barney or whether it's just a regular old plain Jane measuring microphone. Your hearing is key when you're figuring this out. Okay. Now, that is going to cover all of the Butterworth Linkwitz Raleigh filters, 12 and 24 dB, and how to determine crossover points. Now, there's a filter in this system that I am a huge proponent of. I love using this thing because it solves so many problems. It's called a notch filter. Now, what the notch filter does is it attenuates or cuts frequencies within a very specific range. All the other frequencies are going to be unaltered around it. Basically, what we're going to do is we're going to cut a notch out of the frequency response. That's exactly what this does. And normally, these filters are applied to a very narrow range of frequencies. It also means that normally they have a very high Q factor, which means it's a very, very narrow amount of energy that we're going to be working with. Now, these notch filters, you can remove a single frequency or you can remove a narrow band of frequencies. In car audio, these filters can be used to remove door panel resonances, which I do constantly. If you take a tone generator and you sweep the door, the bass drivers, you'll find that more than likely there's going to be a frequency in that door that's going to be 5 to 10 dB louder. You can find out what that frequency is, build a notch filter for that frequency, turn it on, and the frequency, and it kills that door resonance. Same thing in the dash. If you can find a dash vibration or resonance, you can do the same thing. Any of the plastic panels in the car, anywhere in the car, you can get rid of them. You may also use them to lower the chime output in the car. How many times have we all hooked a car and built a system and the stinking chimes are so loud, it drives you up the wall? You can use the notch filters to get rid of the chimes, or at least attenuate the chimes and turn them down. Okay, that's just a few of the ways. Now, what does this filter look like and where can it be found in the Moscone GUI? Well, if you open the GUI up and you see where the crossovers are, you see the high pass and the low pass. If you take a look, you'll see over here to the right, there's these filter areas can be opened up. And you see where it says flat, high pass, low pass, high pass, high shelf, low shelf, EQ, and notch filter. So if you select notch filter, you see now that you have a variable Q, which means you can widen the amount of energy that we're going to work with, or you can narrow the amount of energy with this slider, and you can choose the frequency you wish to work with. Now, in this particular instance, I'm going to show you what a notch filter looks like. That's a notch filter at 1,000 hertz with a Q of 25, if I remember. It's a very narrow amount of energy that has been removed. Everything else is playing from 20 to 20,000 hertz. That's what a notch filter looks like, okay? Now, the Q factor I want to get into because a lot of folks don't understand what that means. And I get it because there's an awful lot of people that don't understand it. And it's one of the biggest influencers of sound quality in car audio, because if we don't use it correctly, you can end up boosting signal or cutting signal way too much. And you end up with something that sounds terrible, or you might actually add too much energy and you can blow a driver. So we don't want that to happen. So The Q factor as it applies to a notch filter is like this. In the car audio environment, it's a horrible place to try and make things sound good. You've got things that ring, vibrations, resonances. There's a lot of unwanted noises in the car audio. Now, for instance, and this is a picture in my particular vehicle. There's a 1,000 hertz resonance, and I mean it is on the nose in my vehicle. It's 1,000 hertz resonance in the dash. That's what it is. So, how did I get rid of it? So, this is how this was done. So you can see here's my 1,000 hertz resonance. And this is what I did. So I tried 1,000 hertz notch filter with a Q of 5, which was 200 hertz bandwidth. Now, you take a look at the amount of energy right here. You see how wide the energy is right here. And you look at how wide the energy here is. Now, I have cut, this takes too much away. So what happened was I narrowed the Q to a Q of 40 with a bandwidth of 25 hertz. And you notice that this and this virtually match each other, and you can see how much I've attenuated it. So this frequency was cut immediately and it went away. That's the difference between a Q of 5 and a Q of 40. Okay, and I hope that explains it for you. And if it didn't, at the end of this, please talk to me and we'll try and get that sorted out for you. So Q factor in the use of an equalizer, okay, this is about the same thing, but the Q in an equalizer is one of the best tools that we have, and it allows you to fine tune a specific portion of the spectrum to achieve the desired sound effects, okay? You can narrow it or you can widen it depending on how much energy we need to work with. And it can and we need to focus on a certain specific area within the frequency response range. So paragraphic equalizers, which is what we have in the Moscone GUI, we can change the Q factor. We can go from a Q of 0.5, which is extremely wide amount of energy we're going to be working with, or we can go all the way to a Q of 40, as you saw with the notch filter. And it's a measure of how wide or narrow the frequency band is. It's affected by the equalizer filter. And basically, it's a ratio of the center frequency to bandwidth, okay? So if we have a high Q factor, it means the EQ filter is going to be very narrow. And if we have a low Q factor, it's going to affect a wider range of frequencies. So as you can see, this is what the graphic equalizer, and that's a paragraphic. And you can change the Q factor, which you can look at right here. You can see it says a Q of 4. All of these can be changed and made from a Q of 0.5 to the Q of 40. This will be the left-hand side of the car, and this will be the right-hand side of the car. You can lock them together, or you can unlock them, and you can literally tailor the car to any type of desired sound that you're looking for. That's what is so powerful about these equalizers in the car. Now, I'm going to give you an example of the Q factor, okay? You take a look at one of them here on the left. This filter is a very, very wide band. This is a Q of 0.5, and I've turned all the energy down minus 12 dB at 1,000 hertz. So you can see this is 1,000 hertz, but you can see the amount of energy either side of 1,000 hertz that we are affecting. Yeah, this is very, very wide, and it affects a lot of energy. Over here to the right, you can see what I did. I basically built what is known as a notch filter right here. This is minus 12 dB at 1,000 hertz to Q of 40. So instead of minus 30 dB, which the notch filter would do, I just turned this down 12 dB at 1,000 hertz. This gives you an example of what goes on and how this works. And you can vary this. You can vary this from a Q of 1 all the way to the Q of 40, and you can widen it or narrow it as you see fit when you're shaping the EQ filters and you're looking at the overall frequency response of the vehicle. Now, if you take a look, this is the acoustic frequency response curve before we equalize anything in the car, okay? So what we want to do now is this. When you use the EQ, the first thing you want to do is you want to remove all the peaks. You want to cut as much of them as necessary. Take a look at that first. Then if there's any broad dips or any broad rises, you want to correct them. Then if there's anything left, you correct any small dips, but you really and truly want to try and limit it to plus 3 dB. When you go like to plus 60 or plus 9 dB, then you have an opportunity to cause problems because we're throwing a lot of amplification power at that one frequency, and you have a tendency you might want to clip a frequency, which you don't want to do. So the results that I did when I removed all the peaks was 400 hertz. I did that a broadband 400 hertz. Then I took 6300, 800, and 100 hertz, and I raised them 3 dB. And as you can see, this is the bandwidth Q of 4. That's the normal bandwidth of a standard parametric EQ or paragraphic EQ. So that's the first thing I did. Now, second round of equalization is this. Okay, this is the results that we did. This is what I ended up with on the second one. I took a look at this peak at 200 hertz, which I turned down 1 dB. Then I saw 1600 had a problem right here. See this broadband amount of energy. I raised it 2 dB, but you notice that I lowered the Q factor. So this amount of energy right here has been raised 2 dB. I also had a problem in 8,000 hertz. You can see it right here. I raised 8,000 hertz 3 dB with a wider Q, and then I boosted 20,000 hertz with the Q of 2, and I got some more energy out here. So this is the equalization that you can do, and you can do it really easy, and it's not hard. Nick, we got to do more. Yeah, I'm going to do more because this is the second round, and then here's the third round. And as you can see, this was not that hard to do. You go back and take a look. I had a slight dip at 55. So we corrected it. I had a slight problem at 2,500 hertz. We corrected that. I had a slight problem at 6,300, and we had a slight problem at 12.5. Now, this gets me a ruler flat response curve. Is this going to sound good? No. But right now, that allows me to listen to the system, and I can go and fix it, and I can shape it the way I want to as far as what my hearing tells me. Now, this is assuming you guys do not have Barney. You have Barney. Barney's going to do all this for you. This is how Barney works. This is exactly how Barney works. Okay? He just does it for you. So if you have the opportunity to use Barney and you haven't gotten one yet, please do, because it makes life so much easier and you don't have to go do this. And I will tell you, I haven't done this in a while because I use Barney all the time. But for those of you that don't have access to Barney yet, this is how you do it. Now, there's some more filters in here that we have called the high shelf and the low shelf. And what these shelf filters do is it allows the boosting or attenuating either the high end or the low end of the frequency spectrum that which we want to choose to work with. The shelving filters boost or attenuates the high end of the frequency spectrum known as the high shelf, and the low shelf does the exact opposite, okay? So with a low shelf filter, that's used to boost energy or lower energy below whatever frequency we choose. So if you take a look, this is a low shelf. This is at 80 hertz. This is plus 6 dB with the Q1. This is a ton of energy that I've added to boost 80 hertz in the subwoofer. The cool thing about these shelving filters, okay, is that if we have built our crossovers and we've done all of our work, I need some more energy in the subwoofer. And when I turn this up, it will not affect the phase angle between the sub and the mid bass driver. If we have gotten it correct, this does not affect any phasing whatsoever, either turning it down or turning it up. Yeah, that's the beauty behind the shelves. It allows you to do that. Okay. So a high shelf is the exact opposite. So you can see at 5,000 hertz, I turned it down 10 dB, or I raised it 9 dB with the Q1. It is really, so if you've got, for instance, a tweeter that has off-axis response that dies above, let's say, 8,000 hertz, which a lot of tweeters do in cars, you have the ability to say, you know what, I can just take a high shelf filter. I can take it at 5,000 hertz and I can boost it 9 dB and I can get all the energy back, or a lot of that energy back. Same thing if you get a nasty reflection off of the windshield and you got something boosted like, 8,000 hertz, 9,000 hertz, 10,000 hertz, and it sounds terrible, you can build another high shelf filter and turn it down. And that way, acoustically, things sound way, way better. Okay, that's what the shelves do. Now, these benefits, again, it's really easy to achieve the tonal characteristics a customer may want. If they want things less boomy, then you would use this low shelf and you would lower the mid bass transition to the subwoofer. If you want things to sound brighter, obviously you're going to use a high shelf on the tweeters. There's a lot of different ways of using it. There's particular frequencies, that are too far off axis. The mid bass driver in the door, for instance, it rolls off faster in the upper frequencies than the mid bass in the passenger side door. Okay, this is what we can do. The black line to the red line, that's the bandpass filter of 63 hertz to 400 hertz. And then I added this is a shelf. I added a high shelf at 63 hertz. And you can see what happened. The off-axis response of the mid-bass driver came up so that it matches the off-axis frequency response and the on-axis frequency response of the mid-bass driver in the passenger door. That is the key to this whole thing. That's the way these things work. That's the way you can see it right here. Okay. I added 2 high shelf filters. I added one at 150 hertz and I added one at 1,000 hertz, and I turned it down a little bit. So you can see this is the mid-bass driver in the door on the left. This is the off-axis response. This is the mid-bass driver on the right. And you see what we did here. I added a high shelf filter at 150 hertz, and there's that Q factor again. I raised it plus 7 dB, which is right here. So I raised it, and you can see all the energy it added to it. And then I wanted this black line to match this one. So at 1,000 hertz, I turned it down 4.4 dB, and this is what I ended up with. And that's before any equalization. That's before anything else takes place in the car. Okay. So this makes things easier as far as building crossover networks are concerned. Okay. That's the reason why these filters, these high shelf filters, are so powerful. And they're found in your crossover frequency range section of the GUI. Okay. Now, if you want to correct deficiencies in high frequency response, take a look at this. This is a high pass filter that we built at 3,000 hertz. It's in minus 12 dB, left and right. The black line, this is the tweeter on the left, and the red line is the tweeter on the right. So in order to fix that, I built a high pass shelf. This is a high shelf using this right here. All we did was boost frequencies, 5,000 hertz, 8,000 hertz, and 12,000 hertz. And now this is what the frequency response looks like. So they virtually match each other. That's how you use these filters. That's how you use a shelving filter. And they are lifesavers, okay? You can also increase sub-bass output, and it's an ideal situation to use a low shelf, okay? And again, when you use these, they don't shift phase. So when we are sitting here, Dan, we've got somebody that wants to have more sub-bass in the car. After you've tuned the car, they want more sub-bass. Well, instead of turning the sub-bass knob up and adding more energy to it and shifting the frequency response beyond the 80 hertz crossover filter that we're using, all you do is go in and take a low shelf filter and boost it with a Q1 of 7.5 dB. So now the customer is really happy. He's got his bass response, and and the phasing remains the same. So nothing changes. So all of the energy, the impact, the drive is still the exact same, and there's no smearing of energy in the car. And that's basically what it looks like, low shelf. Okay. So if you don't use the low shelf, remember I said if you turned it up, this is what happens. Well, there it is. You can see it right here. the frequencies change, okay? So if you take the red line and you turn the bass up, you notice that the crossover has changed all the way over to 100 hertz versus 80 hertz. That's the reason why you want to use a filter such as a shelving filter, okay? So I made it. Thank you for attending. Thank you very, very much. I appreciate your time. And at the end of this, if anybody has any questions, we'll be more than happy to answer them. Thank you very much.